Warm greetings to all. I am Dr. M. Balaji, Assistant Professor of Physics, Saurashtra College, Madurai, Tamil Nadu. I am a participant of MOOCs 32. Today I am going to discuss about the introduction of magnetic nanoparticles. In general, magnetic materials are classified in three different types. One is diamagnetic material, para and ferromagnetic material. In general, these diamagnetic materials are called as non-magnetic material because even in the presence of high magnetic field that won't give any magnetization value. That's why which is called diamagnetic material. But in the case of paramagnetism, we can get magnetization value but only in the presence of high magnetic field. In the low magnetic field, that won't give any magnetization value, but in the high field which gives the magnetization value. In general, the magnetic properties are identified using the susceptibility parameter mu. The susceptibility value, which is nothing but the magnetization value divided by the how much field we are applying on that. So applied field value, which gives the susceptibility value. In general, the susceptibility value for the diamagnetic material which is negative, because as I said, which won't give any magnetization value and which revert the direction of the applied magnetic field. That's why the susceptibility value is negative and it's in the range of 10 to the power minus 5. But in the case of paramagnetic material, the susceptibility value is positive and which is in the order of 10 to the power minus 2 to 10 to the power minus 5. The one more type is ferromagnetic material. These ferromagnetic materials, number of atoms are coupled together and which creates the domains. All these domains are aligned in a same direction. So when you apply the external magnetic field which gives the magnetization value, and even more in the absence of the field also which gives the magnetization value because of the internal magnetic dipole moment. These ferrimagnetism and antiferromagnetism also branches of the ferromagnetic materials. Here the atomic alignments are aligned anti-parallel to the direction of the magnetic field when we applied that on that, and in the ferrimagnetic material the positive spin which is not equal to the negative spin. So but all these three, ferromagnetism, ferrimagnetism and antiferromagnetism, gives the hysteresis behavior. Before we going to see the hysteresis behavior, the general MH relationship for diamagnetism, here the H is the applied field direction and M is the magnetization direction. For diamagnetism, as I said, which gives the negative magnetization value, so there is no magnetic field at all even in the high magnetic field, so which gives the negative impact. But in the paramagnetic material, at the high magnetic field H, which gives the magnetization but which is very low. But in the case of ferromagnetic material which gives the hysteresis behavior, the atoms are aligned on the direction of the magnetic field up to that saturation magnetic field, then which comes to their original position. In the case of ferrimagnetic material, the similar, almost the similar trend which gives, but the value of positive of which may not be equal to the negative of. It's the hysteresis plot for ferromagnetic and ferrimagnetic materials. Here, in the absence of the external magnetic field which are initiated at the 0 point, then when we increasing the applied magnetic field on the material, continuously the magnetization value which is increased linearly and up to that saturation magnetization value attained which is continuously increasing. Then when we removing the field which continuously reduce the magnetization value up to this remnants value, then which comes to the zero magnetic field which comes to the coercivity value, then again the similar trend which is obtained on the negative direction also, right? So these three important parameters which distinguish the magnetic behavior of the material: saturation magnetic field, remanence, and coercivity value. The saturation mu s value which gives where we can utilize these materials. In general, these hysteresis behavior, like ferromagnetic materials, are classified in two different types: soft magnetic material and hard magnetic material. Mostly we are using these materials in the memory devices, so that is mainly because of the variance of the coercivity and remanence saturation value. Remanence value, which is nothing but the in the zero magnetic field value, how much the residual magnetization value which are presented on this material, that is called remanence. The coercivity, which is nothing but even in the absence of the magnetic field, how much value, internal magnetic field value, that is the field required to reduce the magnetization value into zero, that is called coercivity. So these three parameters generally distinguish the hysteresis behavior of the ferromagnetic material. Here we are going to discuss about the nano superparamagnetic material. The superparamagnetic material that won't give any coercivity or remanence value, exactly, which is initiated at 0 point. When the material goes below to that critical size, the ferromagnetic materials are converted into superparamagnetic material. Here we can see the example: the same material, the same iron material which has the hysteresis behavior and the coercivity value is 52 Oersted, but when the size goes 12 nanometer, the iron oxide nanoparticles which are converting into superparamagnetic material. These superparamagnetic materials are mostly used in medical applications, which are combined with the polymer material and some composite materials, so which is very much useful in cancer diagnosis, drug delivery system, and hyperthermia treatment. Particularly in tissue engineering, these superparamagnetic materials are currently useful. Thank you one and all.